So now we're going to move to a series of short talks by the early career scientists. So for this, it's going to be 4 minutes talk, and I will give 1 minute warning for everyone. So James Brown talk about Cepheids.
Okay, thank you. So my name is James Barron. I'm a PhD candidate at Queen's University working with Greg Wade. I'm not going to talk to you about strong magnetic fields. Instead, I'm going to talk to you about very weak magnetic fields, observations we've been doing with Barron over the past 3 years, trying to provide a first characterization of magnetic fields of Cepheids in the instability strip. So I'm going to start just by reminding everyone that Cepheids are a crucial link between the fields of cosmology and stellar astrophysics. Their period luminosity relation makes them important distance rulers in the cosmic distance ladder. In terms of stellar astrophysics, the instability strip region marks the transition between the primarily radiative envelopes of the Cepheid B star progenitors and the deep convective envelopes that form when these stars transition across the instability strip to the red giant branch. Indeed, these stars will make several crossings of the instability strip within blue loops, in which their internal structure will change. And we have a poor understanding of how magnetic fields are sustained, created, or destroyed during this process. The first detection in a classical Cepheid was by Jason Grunhut in 2010 in Eta Aquilae, which was followed up in this series of observations across the full pulsation cycle. What's plotted here are the Stokes-B profiles, and if you're familiar with LSD Stokes-B profiles, you'll notice that these do not look like normal Zeeman signatures. These signatures are distorted by the pulsation of the star. And so what we've been trying to do is work on ways to model these types of signatures and understand globally what Cepheid Stokes-B profiles look like. So we've been conducting a magnitude-limited survey of 26 of the brightest classical Cepheids using primarily Espadon, but also HARPS-PUL on the ESO 3.6-meter telescope for the most southern targets. We've detained 14 total detections, which I've shown a sample of here, and their places in the instability strip. We observe a wide range of complex Stokes-B morphologies that show asymmetries, indicating that these profiles are distorted by magnetic field gradients in the atmosphere. These observations are technically challenging because we require sub-Gauss precision, and we can only, for maximum efficiency, we need to observe near photometric maximum, which means CFHT is excellent because we can do acute observing and only observe near these specific phases and in the best observing conditions. I'll also point out that when we obtain ultra-high signal-to-noise, we have detections in 10 out of 12 targets with Espadon. To finish, I'm just going to show you two interesting cases. This is a magnetic detection we have in this type 2 W Virginia Cepheid Kappa Pab. This is a little bit of a different object. It's about 0.6, 0.7 solar masses. You can see this blue shifted profile here with this amplification in the Stokes-B profile. We think this is related to the phase where we've observed the atmosphere of the star collapsing while the lower atmosphere is increasing, and we have a shock magnification in the profile. I'll finish here by showing observations we have obtained over the past few years of Polaris, trying to measure its rotation period. This has been challenging due to the limited number of mountings Espadon has every semester, but with enough observations, we now believe we have good evidence that the rotation period of the star is about 100 days, and over 12 or so rotation cycles, the field has remained stable at a sub-Gauss level, which is giving us some indications of the origin of the field and its stability. And I'll just finish by leaving my conclusions here. Thank you.
Any questions for James? Okay, if not, let's move to our next speaker, but thanks, James, again.